Suranjit has covered. So I think he must have covered the concept of energy release rate and the stress intensity factor K1 and how to relate K1 to G, etc.
Yes, sir.
And what else?
Sir, various theories regarding that, and that's all the three modes which is more dominant in what phase, and while evaluating the fracture, then what all comes in which zones. Those are meant.
Okay. So Irwin's correction also he must have taught you, right? Irwin's plastic zone correction. Irwin's concept, Griffith concept.
Sir, only Irwin's, I guess, sir, not the Griffith.
Okay. Hello? Irwin's concept he has taught, right? Hello? You are able to hear me?
Hello? Hello? Sir?
You are able to hear me?
Yes, sir, yes.
Okay. So then I will extend this, the portion of fracture mechanics, that is plastic zone shapes and correction. Okay, and there will be some little bit repetition, but this is only to maintain the continuity. And this PPTs, the slides that I will presenting, I will send to you, all of you, so you can go through them before for the next lecture. So every day we will be covering that 11:30, 12:30 will be taking the lecture. Okay. So if any of the concepts, you see this subject will be very new to you. Okay. You may not have gone through India previous BTech or even similar topic. So it may be slightly difficult to follow, but don't worry. You try to understand what is covered in the lecture. And you ask me if you have any doubt, you can ask me in between. You can also later also ask me. I have given my phone number and email ID in the starting slide. Okay, you can so you can contact me anytime if you have any doubt. Okay, so let us start. Okay. Hello. Any of you can tell your name? One is I can see Mayank, Unduru. Okay, so now who was talking just now? What is his name?
Sir, I'm Vedit.
What is your name?
Vedit, sir. Sir, you can call me ready.
Okay, ready. Okay. So let us start. Okay. So I will start with the energy balance, basically energy release rate concept. So this you must have studied the concept of energy release rate, right? Ready?
Yes, sir.
So this is can you explain me what is Griffith criteria, Griffith energy release rate concept?
Griffith has not been taught, sir. Only Irwin has been taught.
What Griffith is starting, later it will be Irwin will be correction. Starting is Griffith concept, energy release rate concept.
I exactly don't know.
Okay, you do not. Okay, no problem. Okay, so I will also cover that. So from the I will just go through the basic concept. So in fracture mechanics, anybody can tell me how fracture mechanics is different from other solid mechanics. You have already studied the strength of materials, right? Concept to design the components or to study the stress pattern in the components. So what is the difference? Why you cannot use strength of materials? Why you need a different branch, fracture mechanics? Can anybody tell me? Because
yes, sir, at lean fracture, the stress is coming out to be infinity, but in reality, the fracture creeps even before the yield. So that was the reason we'll have to calculate exactly how much stress we'll have to put, whether not the crack to profit.
Okay. So this is correct, but there are other things to it. See, one is the design by stress. Okay, for example, when you do the design of your shaft, design of a beam, okay, or design of any component, pressure vessel or something, you see how much is the how stresses are coming because applied load. Then you apply different theories of failure, right? Like principal stress theory, von Mises distortion analysis theory, okay, the stress criteria, etc. to check your the failure criteria, and their failure can be either yielding of material or brittle fracture. Your stresses below a limit, below a value, okay, that is allowable value, okay, with some factor of safety. Now, as you are told correctly, but this is for materials which are perfect. There is a continuum, there is no defect. Once you have a defect or crack, okay, and especially when the crack is very sharp, okay, and you know that initial for a elliptical kind of a defect, you can calculate the stress, and you know that for a circular defect, that stress is elevated by 3 times. That is stress concentration factor equal to C. For elliptical crack, the stress concentration factor depends upon the root radius. Okay, it is inversely proportional to the root radius. So if root radius is very small, the stress concentration will be more and more stress concentration. Okay, so for a crack which is a very sharp crack, infinitely sharp crack, there root radius will tend to 0. So then your stress is singular. Singular means it is tends to infinite or the near to the crack tip. Okay, so the stressless concept you cannot apply, and in reality also the material, okay, it cannot take the infinite stress. So material will start to yield locally, and even also it, suppose if it is a brittle material, it will not yield, it will start fracture. Okay, but the fracture will not occur immediately. Okay, because the radius is never 0. In case of materials, material consists of atoms and atomic arrangement. So that is the radius is not 0. The radius is nothing but the interatomic distance. That is the minimum radius you can get. Okay, so you must have studied theoretically. Suppose there is no defect. Okay, and then if we calculate the theoretical strength of material, this is actually very very high. Okay, but because of the defect etc., that is we can the strength reduces, and moreover in the presence of the crack, the stresses at the crack tip get elevated. Okay, so what is more important is that Griffith did many experiments. Okay, in the military material like glass. Okay, he was the first one in 1920s. Okay, during the World War, he was doing his World War One. He was doing his research. So he saw that he came with the concept that stress at the crack tip. Okay. That of course that governs the failure, but what is that suppose you are applying a remote stress sigma, okay, so and now it's for different crack length. So he saw that the sigma all the failure of the glass was governed by a product of sigma and root over of crack length. Okay. So that was found to constant. For example, if the crack length is more, he found the stress, remote supernatal stress, that is the nominal stress or remotely applied stress. Okay, it is not stress at the crack tip. Stress at the crack tip will be very high. Okay, so he saw the product of sigma and root over A is the crack length, is equal to constant. And this parameter, okay, the product of sigma and root over A, he found. Yes?
Are you sir currently referring to a slide or something like that? Because I think slide is not changing in the presentation.
Slide you are able to see?
Sir, which slide are you referring right now?
I'm just giving you introduction before I come up with the energy balance, because I think it was already covered by Mr. Soranjit.
Okay, sir.
Okay, so I'm just giving you the introduction before I come into this slide. So this slide is still the energy balance. Okay, so I am talking just the concept. So this I think you must have known. The Griffith criteria was that product of remote stress or nominal stress I call, which is very different from, which is not same as the crack tip stress. Product of remote stress and root over A is the crack length, was constant, and he called it is a stress intensity factor. Okay, and then depend upon the type of loading or geometry, that is a geometry factor F will be multiplied. So sigma root over pi A, okay, pi is a constant, root over pi A into some geometry constant into some geometry factor. this was constant for a given material, okay, and it's for the brittle material, and he called it the failure at which this material crack propagates, and in case of brittle material, crack initiation is propagation. So okay, once crack initiate, it will propagate and failure occur. Okay, unless there is some other mechanism or other distribution mechanism is there. Okay, so he called it stress intensity factor. So the concept of stress intensity factor is that you don't look at the stress at the crack case, but you calculate, you look at the value of the stress intensity factor, which is something called a crack tip loading parameter. Okay, so instead of using a localized crack tip stress as the criteria, design criteria, for fracture mechanics, it is more important to evaluate this stress intensity factor. Okay, so suppose there are two geometries having different loading condition, different crack length, but if the stress intensity factor is same, that is K1 is same. Okay, so you can say that these two geometries are equivalent. Okay, so that is how the concept of stress intensity factor is same, and it comes from the energy release rate. Later, he also correlated the stress intensity factor K with the energy release rate, that is the G. So you know that G equal to K square by E. Okay, for plane stress problem. So that means what is energy release rate? Suppose that is a crack in your body and you are giving some energy. Energy how you are giving? You are applying some load or applying some displacement. You are stretching the body. Then the energy that you are giving, okay, where it is going? It is going to suppose you are applying very slowly. So kinetic energy is negligible. Okay, it is almost zero. So it is going as a potential energy into the body. That means it is getting stored as a strain energy. Okay, in the body. Now, when the energy that is you are giving to the body, okay, and it exceeds, then what happens in case of brittle material? So it will try to stretch the atoms apart, okay, and for creating a crack, okay, it needs a surface energy. That means when initially the atoms are together, when they move apart, okay, new surface, stress surface is created. In fact, two surfaces are created. So this amount of energy that we are giving, if it exceeds the surface energy, okay, then the crack will propagate. Okay, that was what are the criteria. So provided I know other mechanism, distribution mechanism. If there is a plasticity, then some energy that we are giving, that also will go into the material as plastic deformation. Okay, and which will be finally be converted to heat energy. Okay, so this concept energy balance which Griffith started, so this can be generalized as the following. So the external work that work I am giving, okay, W dot is related to this is per unit that rate per unit area or per time I can also say. So that is goes into the four the things. One is the elastic strain energy UE, other is the plastic strain energy. Okay. Third one is the kinetic energy, and I told you if you are applying load at a very high rate, then there is some kinetic energy also will be there. But if you are applying load very slowly, this is kinetic energy will be very small. And the fourth one is the surface energy. Okay, so this energy, surface energy, it depends upon the material property. Okay, it depends on the type of material. For example, glass, there is some surface energy, or some other kind of, if it is a material like cast iron, it has different property. It is a material property. So from this energy balance, okay, that is how much work is providing and how much energy the material is to either storing or using it to break the bond. This competition will lead to, will tell you whether crack is happening in the material or not. For example, if your applied work is insufficient, okay, then compared to the surface energy, then crack will not propagate. Okay, so now here all and I can always write using chain rule. I make d by dlt of any. Here bracket means it can have external work UE etc. I can make del by dl into del by dlt. So A is the crack length. So finally the energy equation, okay, and del A by del T is nothing but crack rate of crack propagation. So that becomes common everywhere. So I can write the energy the del W del A. So that is what is called energy release rate. So when it tells rate means per unit area.